So we had done the mathematical modeling part of electrical system. Students,
Yes, ma'am.
Ravi Bali? Yeah. So can you see the presentation?
No, ma'am.
No,
No,
ma'am.
ma'am.
All right, let me show you. Can you see it now?
Yes, ma'am.
Yeah, ma'am.
Okay. So this is the slide on which we were on the last class. So basically, this is how we form the mathematical modeling of electrical system. That is very easy, and you have done this in your circuit theory and other courses. So this is a problem in which you can solve. So let us start the mathematical modeling of mechanical systems. So mechanical systems can be modeled using there are two types of motions in mechanical system. One is translational motion and the other one is rotational motion. Okay, so translational motion is the motion movement of mechanical bodies from one distance to another distance. Okay, so it is linear travel. So that is called translational. So when a mechanical system is rotating, so then in that case it is called the rotational motion. So first we will do the translational mechanical systems transfer function. So how to model a translational mechanical system by a transfer function? You have to take the analogy of electrical network. Mechanical systems have three passive elements, just like as electrical system. These are spring, the mass, and the energy storing element, viscous damper. Okay, so this table you can draw in your notebook. Write down today's date and start noting down the class notes. So this is the first table of mechanical systems in which a mechanical system is used to model the mechanical translational system. So first element is a spring. The spring is attached to a rigid wall and it is stretched with a force Ft so that it travels a distance xt in this direction, and the spring constant we are taking as k. Okay, so force velocity in this case, if you drive the force equation, so it is Ft is basically k integral v tau d tau, where v is the velocity of the spring and x is the distance of the spring. So if you integrate the velocity, you get the distance, as you are familiar from your basic physics knowledge. Okay, so Ft, from this equation you can drive this equation. Ft is k xt, and the impedance, if you form the analogy between electrical and mechanical system, so Ft is basically kxt, where Vt is Rit. So you can say that the impedance of mechanical system ZMS is basically Fs upon Xs, and that impedance is represented by spring constant K. Okay, so the other element which is of importance for mechanical translational system is viscous damper. So it is a basically piston inserted in a cylinder. So the force by which this distance is stretched in this direction, is pulled in this direction, xt, is Fv, and the spring constant, damping coefficient is Fv. So Ft is basically Fv into Vt, where V is the velocity by which this piston is moved in this direction. Okay, and since you know that Vt is basically first derivative of the distance xt, so you can formulate the relationship between Ft and xt as Ft is equal to Fv dxt by dt. Now if you find the impedance, then it will be Fvs. If you take the Laplace transform, so it will be Fs is equal to Fvs xs, right, as we have done in the electrical systems. So if it basically the impedance in this case is Fvs. All right, the third element which is of importance is the mass. So mass of value capital M if this mass is pulled in this direction of xt with a force ft, then the force velocity equation is written as ft is equal to m dv by dt. This is basically Newton's third law. F is equal to ma, right? So now replace vt with help of xt. The relationship between vt and xt is vt is equal to dxt by dt. So dvt by dt is d2xt by dt2, second derivative of xt. So ft is m d2xt by dt2. So if you take the Laplace transform, the impedance becomes ms square. All right. So you can note down this and you can see that the symbols are in ft is newtons. ft is expressed in terms of newtons, xt in terms of meters, vt in meter per second, k is newton per second, newton per meter is the spring constant, fv is the damping coefficient or coefficient of viscous friction, ns by m, which is newton second per meter. M is the mass expressed in terms of kilograms, and if you write it in terms of newtons second square per meter from this equation. All right. Now, like electrical networks, impedances can be defined for mechanical systems, which can be used to write the equation of motion and find the transfer function without bypassing the differential equations. So if you take the Laplace transform of force displacement column of the previous table, we obtain for spring, it is Fs is equal to Kxs. For viscous damper, it is Fs is equal to Fvsxs. For mass, Fs is ms square xs. And if we define impedance for mechanical component as Fs upon Xs as Zms, then you can find out Fs upon Xs, it will be K in this case, Fs upon Xs, it will be Fvs for viscous damper, and K, Fs upon Xs is ms square for mass. So by applying the definition to the last equation, we arrive at the impedances of each component as summarized in the table. So the impedance concept allows us to write the force displacement relationship for mass and viscous damper algebraically as in case of spring. Translational mechanical systems transfer function can be found out by following the following steps. Assume a positive direction of motion, for example, to the right for each moving body. Second step, draw a free body diagram for each moving body and placing on it all the forces that act on the body either in the direction of motion or opposite to it. Step 3, use Newton's laws to form a differential equation of motion for each moving body. Then by summing forces and setting the sum equal to 0. Finally, assuming 0 initial conditions, we take the Laplace transform of each differential equation, separating variables and arrive at the transfer function required. So let us take an example. This is the example. Okay, find the transfer function xs upon fs for this system. Okay, so I want you to note down the diagram, start the problem, and take the notes. So first step is to take a positive direction of displacement. So we have taken this direction, and this is the direction of force. So draw these diagrams in your notebook. Begin with drawing the free body diagram, right? So how do we draw the free body diagram? We take the mass and we see how many forces are acting on this mass. Okay, so mass is being pulled in this direction with the force Ft, which is the external force. So this force, according to Newton's third law of motion, every action has a reaction. So this force is being uh, resisted by all these forces, because this is a system which is being pulled in this direction. So all these forces will act in the opposite direction because of Newton's third law. So this mass m is attached to this wall through this spring and a damper. Okay, so the spring force in the opposite direction will be kxt, The damper force in the opposite direction will be Fv dxt by dt. And the force of inertia force in the opposite direction is m d2x by dt2, which is the inertia force. F is equal to ma according to Newton's third law of motion. All these forces are countered by this externally applied force Ft to move this mass through a distance xt. All right. So if you take the Laplace transform of this whole system, you get this k xs. Laplace transform of dxt by dt is s xs. Laplace transform of d2x by dt2 is s square xs. Right? So xt is replaced by xs, ft is replaced by fs. Right? So if you represent this system with the help of a block diagram, you write the transfer function, you take the input as fs and output is xs. So what is the meaning of input and output variable? Input variable is the variable by which is the externally applied force on any system, and due to result of this externally applied force, what is the resultant which we are getting in the system? It is the distance traveled by this whole system in this direction. So output variable is xs, input variable is fs. Okay, and the transfer function of this block, the equation written in this block is the transfer function of the block of the system. Okay, so output upon input, that is xs upon fs, is the transfer function which we write in this block. So we drive the transfer function like this. Yeah, I want you to take the notes. We write the differential equation of motion using Newton's second law to sum to zero the different forces acting on the mass to yield this equation. So can you see this equation? Because this is the first force from the previous free body diagram. If you write Ft is equal to kxt plus Fv dx by dt plus m d2x by dt2, right? Because this is the force in this direction, this is the opposing forces. So this force, if this force overcomes all these three opposing forces, then there is a translation of xt, right? So Ft becomes equal, should be equal to or greater than this force. So Ft is equal to all these forces. This is what I have written here, right? M d2x by dt2 plus Fv dx by dt plus kxt is equal to Ft. Now the second step is take the Laplace transform and assuming zero initial condition. So if you take the Laplace transform, you get m s square xs plus Fv sx plus kxs is equal to fs. So you can take xs common, so you get ms square plus fvs plus k into xs plus equal to fs. So solving for the transfer function, which is transfer function is output upon input assuming zero initial condition. So xs upon fs equal to 1 upon ms square plus fvs plus k. And using the concept of impedance, we notice that the Laplace transform equation of motion is of the form sum of impedances connected to the motion at x into xs is equal to sum of applied forces at xs. Okay, so please note down all these mathematical derivations. Problem with multiple degrees of freedom, we draw the free body diagram for each point of motion and then use superposition. For each body diagram, free body diagram, we begin by holding all other points of motion still and finding the forces acting on the body due only in its own motion. Okay, then we hold the body still and activate the other points of motion one at a time, placing on the original body the forces created by the adjacent motion. So let us take a numerical example. So suppose this is the problem, right? We have this system. Okay, so you have to find out the transfer function fx to s upon fs for the system shown in the diagram. So I want you to note down this problem and try to solve this problem on your own. The system has two independent degrees of freedom since each mass can be moved while the other is held still. There are two masses, so take one mass at a time and apply the superposition. So, thus two simultaneous equations of motion will be required to describe the system. And the two equations come from the free body diagrams for each mass. Okay, so you need to draw two free body diagrams, one for M1, the other one for M2. As we have done in the electrical system, I1 and I2. If we have two meshes, then we have two mesh currents, I1 and I2. So here also we'll take X1 and X2 as the two variables, two output variables. Okay, so try to solve this problem on your own by drawing the free body diagram for M1 and M2. Do it yourself. So this was the equation. This is the solution of the previous problem. We had two masses, M1. M1 is being pulled in this direction by K1X1S, FV1SX1, and this Fs is in the opposite direction. If you can see this, we are pulling this system with Fs. Fs is here. We are applying force at this point. So this system M1 is being experienced a negative force K1X and this damper. Because this is a connected system, the effect of this force will be observed with this mass also. So this damper will, this whole system will, this mass will travel in this direction by x1. This mass will, the other mass will travel in this direction by x2, and this is the applied force. So here this the effect of this damper and effect of this spring will be experienced by M1, and effect of this K3 spring and these two will be experienced by M2. So if you write the free body diagram, you can see that there is a force, external force applied to M1 in this direction. Due to this, a reaction force will be developed K1X1S, FV1S X1S, and M1S square X1S. And this, because this is a connected system, we will have FV3SX1, K2X1S, right? So basically M1 is being pulled in this direction by K2X2, FV3SX2. This is basically M1. So M1, total force acting on M1 is this. Okay. I think this is M2. This is M2. This is M2. It is K3 X2S in this direction and FV3 X2 minus X1 K2 into X2 minus X1. Here K1 X1 minus X2 and FV3 X1 minus X2. So like this. If we hold M2 still and move M1 to the right, we see the forces shown in figure at the top on the left. If we hold M1 still and move M2 to the right, we see the forces shown in the figure at the top on the right. The total forces acting on M1 are the superposition as shown in the figure at the bottom. Right? So you can ponder on these forces for a while, and if you can ask if you have any question. So if you consider M2, you can see these are the forces in this direction, and there is a spring for M2 is connected to the wall through this spring. So this is the free body diagram for M2. So you can take the Laplace transform and you can get this equation. So you can draw this diagram also and you can understand better. So if you try to write the transfer function x to s upon fs, you can write down with the help of this equation fv3s plus k2 upon determinant delta. So determinant delta is given by this. Okay, so the last two simultaneous equations of motions are in general form, can be written like this. Okay, sum of impedances connected to motion at x1 into xs x1s, and sum of impedances between x1 and x2 into x2s. So you have to take the difference between the two, that will be equal to sum of applied forces at x1. Similarly, sum of impedances between x1 and x2 minus sign plus sum of impedances connected to motion at x2, in that gives you the sum of applied forces at x2. So if we become familiarized with this form, we can find the equation of motion by inspection without drawing the free body diagram. So you have to practice a little bit and then you'll be able to uh, write the equations just by inspection. Okay, so you can draw this diagram and you can solve this problem yourself. So here the system has 3 degrees of freedom, since each of the 3 masses can be moved independently while the others are held still. So that is the meaning of degree of motion. So that if we keep one body at rest, then the other, how many other bodies can be moved freely, independently. Okay, so it has 3 masses, all of them can be moved independently, so it has 3 degrees of motion. Try to solve this problem just by inspection.
Ma'am, these classical mechanics problems come under control system also.
Yes, because the systems which we will deal in real life are electromechanical systems. Most of the time for control systems we deal with electromechanical systems, right? So
But
having,
but ma'am, this is not electromechanical. This is
it is just
purely.
mechanical. I have done electrical, then mechanical, then I will go to electromechanical afterwards. This is a sequence in which I will move.
Okay, ma'am.
ना, तो अभी आपको पहले मैंने इलेक्ट्रिकल का समझाया, मैकेनिकल का समझा रही हूँ, फिर रोटेशनल, अभी ये ट्रांसलेशनल है, फिर रोटेशनल का समझाऊंगी, फिर उसके बाद वी विल मूव टू द एक्चुअल सिस्टम्स विच आर मोस्टली इलेक्ट्रोमैकेनिकल, है ना. उसमें हम लोग क्या करेंगे, कोई एक मोटर होगी, मोटर कनेक्टेड टू होगी कोई वॉल्व से मोटर को, कंट्रोलर क्या होता है, यही तो होता है ना, कोई वॉल्व ओपनिंग एंड क्लोजिंग है या सर्वो सिस्टम्स हैं, ऑल दीज आर कंट्रोल सिस्टम्स. तो उनका जो बेसिक कॉन्फ़िगरेशन होता है दैट इज इलेक्ट्रोमैकेनिकल. सो यू नीड to understand how to draw the mathematical model of a mechanical system, of electrical system independently, and then the two of them taken together, that is electromechanical systems. तो हम लोग स्टेप बाय स्टेप ही तो चलेंगे ना. ठीक है, आप लोग इसको करिए. तो ये आपका सिस्टम का इक्वेशन होगा. Since we have 3 3 degrees of freedom, 3 masses, m1, m2 and m3, so you will have 3 variables here. sum of impedances connected to the motion at x1 minus sum of impedances connected between x1 and x2 minus sum of impedances connected between x1 and x3. Okay, this will summation of all this will give you the sum of applied forces at x1. Similarly, another equation you will get sum of impedances between x1 and x2 with minus sign, then plus sum of impedances connected to the motion at x2 with plus sign, then with minus sign sum of impedances between x2 and x3. That will give you sum of applied forces at x2. Okay, similarly, the third equation. So M1 has two springs, two viscous dampers, and mass associated with its motion. Therefore, this one is one big spring between M1 and M2, and one viscous damper between M1 and M3. Therefore, we get this equation. You can see, you can drive this equations yourself, and you can verify. So here is another system for which you can draw the differential equation. You can write the differential equation. I want you to write it yourself. So we can move ahead with the rotational mechanical systems transfer function. Rotational mechanical systems are handled the same way as translational mechanical systems, except that torques are replaces the force and angular displacement replaces the translational displacement. Similarly, the mechanical components of rotational systems are same as those of translational systems, except that the components undergo notation instead of rotation instead of translation. Okay, so first component is a spring, but here the output is torque. The force applied to this system is not being pulled in this direction; it is being rotated in this direction with the help of a torque T. And this torque results into a displacement, rotational displacement theta t. Okay, so theta t is the rotation, is the output, and tt is the input torque. So tt is given by k integral 0 to t, omega tau theta. Omega is the angular velocity and theta is the angular displacement. So t is equal to k theta t and the impedance is k. Similarly, viscous friction coefficient having shown as capital D. This system T is given by d omega t and T is d theta by dt. Omega is the angular velocity, which is the first derivative of angular distance. So d theta by dt is equal to omega t. So ds is the impedance in this case. Similarly, if you have a body with inertia j being rotated in this direction by theta t by applying a torque t. So t is given by j d omega t by dt. T is equal to j d2 theta t by dt2. So impedance is given by js square. So I want you to note down this table, and there is appreciate the similarity between translational and rotational system of the mechanical. The symbols are torque is given in terms of Newton meter, theta is measured in terms of radians, omega t, which is the angular velocity, is radians per second, k is the spring constant in terms of Newton meter per radians, d is the viscous friction coefficient given by Newton meter second per radian, and j is the inertia and given by kg meter square in terms of Newton meter second square upon radian. All these units you can derive from these equations. Okay. So let us take a numerical problem of having a translational system like this. Transfer function, you have to find the transfer function theta 2s by ts. Right here, ts is applied to this body having moment of inertia j1, and this results in an angular displacement of j2 by theta 2. So we want to find out the transfer function theta 2 upon ts. Okay. So the rod is supported by bearing at each end and is undergoing a torsion. A torque is applied at the left and the displacement is measured at the right. Okay. So we approximate the system by assuming that the torsion acts like a spring concentrated at one particular point in the rod with an inertia j1 to the left and inertia j2 to the right. Okay, we also assume that the damping inside the flexible shaft is negligible. The schematic of the system is shown in the figure at the right, and the system has 2 degrees of freedom so that it can have two simultaneous equations to solve. Okay, so if you draw the free body diagram, it will be something like this. Okay, this is basically J1 and J2. J1 is being forced to rotate with the help of torque, externally applied torque T, and J1 rotates through an angle theta 1, J2 rotates through an angle of theta 2. Okay, there is a bearing at this point with coefficient friction, the coefficient of viscous friction equal to D1, and the coefficient of viscous friction at this point is D2 or torsional constant. All right, so draw this diagram. So if you draw the free body diagram, it will be something like this. We draw a free body diagram of J1 using superposition. So this is J1. It is being shows the torques on J1 if J2 is held still and J1 rotates only. So this is basically J1 and J2 is rotating in this direction with velocity J1 s square theta 1s and D1 s theta 1s and k theta 1s, right? And the direction of theta 1 is taken, positive direction of motion of theta 1 is taken in this direction. Okay. This figure shows that J1, the torques on J1, if J1 is held still and J2 rotates, is like this. Okay, K theta 2 in this direction and theta 1 in this direction. And this figure shows the final free body diagram for J1, from which the equation of motion is resultant like this. All right, so note down this. So similarly, you can write the free body diagram for J2 like this and write the equation of motion for J2. So using the last two simultaneous equations, the equation of motion transfer function can be written like this: K upon determinant delta. So delta is J1 S square plus D1S plus K minus K minus K, J2 S square plus D2S plus K. So the last two simultaneous equations can take the general form like this: sum of impedances connected to the motion at theta 1 into theta 1 minus sum of impedances connected between theta 1 and theta 2 into theta 2 is equal to sum of applied torques at theta 1. Okay, minus sum of impedances between theta 1 and theta 2 into theta 1 plus sum of impedances connected to the motion at theta 2 into theta 2. That gives you the sum of applied torques at theta 2. So once you become familiar with this form, we can find the equation of motion by inspection without drawing the free body diagram. I want you to take down the notes. So now solve this problem. This is a equation. Find out equation of motion by inspection. You have three bodies with inertia J1, J2 and J3. And there are three bodies connected. They revolve with angular displacement theta 1, theta 2, theta 3. Applied external torque is G. And there are two dampers with damping coefficient D1 and D2. One spring with spring constant K. Okay, three dampers, no? D1, D2, D3. So you can write the equation of motion. Try it out yourself. I will upload this in the Google Classroom. and upload your solution on the classroom today by 11:30. I'm giving you some time. Try to solve this problem and upload it in your handwritten copy there on the Google Classroom. All right. I am leaving this as your assignment for today. To write the free body diagram, I have written do not solve, but you have to solve it. Okay.
मैम कुछ स्टूडेंट्स को क्लासरूम का मेल नहीं आया था, तो आप कोड दे देंगे तो वे भी एक्सेस कर पाएंगे.
Code, class code.
यस मैम, गूगल क्लासरूम का.
I'll write on the chat box here on the
थैंक
Meet.
यू.
Okay. I have written the class code on the chat box. नहीं, डायग्राम क्यों करना होगा? आपको पूरा सॉल्व करना है. समझ में नहीं आया? इसको सॉल्व करना, जैसे मैंने अभी पिछला क्वेश्चन किया है ना, फ्री बॉडी डायग्राम बना के हर एक के लिए अलग अलग पूरा ठीक से जैसे मैंने पिछला क्वेश्चन किया है, सेम वे यू हैव टू अटेम्प्ट दिस क्वेश्चन एंड फाइंड आउट द ट्रांसफर फंक्शन. All right. Any question? Move forward.
मैम अटेंडेंस ले लीजिए, आज फ्राइडे है तो.
अच्छा, आप लोगों को लेट हो रहा है. चलो मैं अटेंडेंस ले लेती हूँ पहले. ओके.
मैम.
यस.
मैम सिलेबस बता दीजिए सेशनल के लिए.
अभी मैं कवर कर रही हूँ ना. लेट मी. अभी तो नेक्स्ट वीक है ना हमारे पास.
यस मैम, एक ही दीजिए.
तो अभी करने दो, थोड़ा कवर करने में थोड़ा कम हो पाया है ना.
No, ma'am, only 10 days left. Control system is our first paper.
हाँ हाँ, तो अभी नेक्स्ट वीक तो है ना हमारे पास.
Okay, ma'am.
अभी क्लास लेने दो थोड़ी सी, बता दूंगी. फर्स्ट यूनिट तो रहेगा पूरा.